All right. Good morning. Good afternoon. Hello, everyone. Thanks for tuning in here to today's webinar. This is webinar with Emicent, of course, and our friends from Technology Support Services from Scan to Solution, how LiDAR is transforming engineering workflows. So just a few notes, little admin before we get started here, just to let you know. The session will be recorded, so anyone can tune in into the future and watch it if they like. If you have any questions at any point throughout the webinar, we will answer them either during or perhaps at the end or toward the end. But please put those in the chat as they come to mind. And then as we're going along, just know that you will be muted. So we won't be able to hear you, but you will be able to hear us. So without further ado, I will introduce our presenters. So I'm Daniel Porter from Emicent. Been fortunate enough for the last, I guess just about the last year to be working with these two gentlemen here, Mr. Daniel Ferrari, the president of Technology Support Services Canada, and Stephen Bruto, the project manager for Technology Support Services. So with that introduction out of the way, I'm going to hand the microphone over to Daniel.
All right, thanks, Daniel. Appreciate that. Hopefully, no one gets confused between the two Daniels. We've got a bit of an overlap here, but certainly excited to be presenting here. I'm just going to start sharing my screen so we can get our presentation up. Okay, hopefully I'm in presentation mode on your end. It seems to be that way on my side. But
Yep, that's good.
Yeah, so excellent, perfect. So I'll jump right in and give everyone sort of a brief overview of who we are and what we're planning to do today. As you can tell from the title for this webinar, we're really focusing the talk on how we're taking LiDAR and specifically our experience with Hovermap and our STX and transforming the workflows in our own engineering environment. And that's sort of what you're going to see today. So I'll give you a little bit about who we are. Technology Support Services is a company born sort of with the idea that there are lots of pieces of technology out there that help support the engineering work and the consulting work that we do. We've invested heavily over the last few years in LiDAR, photogrammetry, infrared thermography, acoustic imagery. So there's lots of different pieces out there that really help us quantify things and give us more sort of efficient and accurate information that we can base our engineering decisions on. And this all came about through our sort of parent company, Technology, TSS Building Science. And this is sort of where our engineering expertise sort of flows from. TSS Building Science, like its namesake, really just deals with all things building related, building envelope, wall cladding, windows and doors, roofing. A lot of the examples, or all of the examples you're going to see today in terms of how we use LiDAR, is all based on real projects that we've completed in TSS Building Science. A little bit of a brief history. TSS Building Science has been around since 1993. It was purchased by myself in 2018. And really the goal with the purchase was to create sort of that industry-leading multidisciplinary team focused on sort of using out-of-the-box thinking to identify, solve, and implement exceptionally creative solutions for our clients. And this technology piece is really a testament to that. Thinking beyond the idea that, you know, an engineering opinion is, you know, where the end all and be all of our decisions comes from. Absolutely, you need expertise, but definitely the technology that's available to us helps us immensely in justifying all of those opinions. And just for context here, I threw a couple of photographs and slides in here about, you know, some of the typical things that we would do as building envelope consultants. We deal with roofing, you know, window renewals, underground parking garage restoration, interior slab waterproofing, parking lot reconstruction and site works, structural assessments, including things like fire damage, like you see on the screen here. Again, this is a very typical sort of representation of what we would do for most of our clients, almost all of our clients, in the realm of building envelope consulting. Well, what we're here really to discuss is sort of what our the original premise was: scan to solution. You know, how LiDAR is transforming engineering workflows. Over the last, I would say, 2 to 3 years, maybe a little bit longer, we've really dove into LiDAR and photogrammetry and similar technologies to help us in our workflows. And what this really means is, you know, from a traditional workflow point of view, engineers and consultants rely on data collection. And a lot of that data collection is manual site measurements, transcribed into sketches that turn into 2D drawings. All of that is based on sort of user input. You would send a consultant or an engineer out to a site to go look at a problem, some sort of an issue, and take down information and come back to the office and collaborate with the team about what the solution looks like. Now, inherent in that process is risk, and the risk is human error. The human error in measuring something incorrectly or not noticing something on site that is sort of pivotal or fundamental to the solution that you're going to develop. And I like to throw this slide in here when we're talking about these things, because this is essentially what gives me anxiety. You know, when I send engineers or consultants out to a site to measure something, and if I send 3 people out with 3 different measuring tapes, I could potentially end up getting 3 different results, just because the basic tools that we might be using or the sort of perspective that the inspector is taking on might sort of render our viewpoints sort of skewed. You might end up with different information when you get back to the office. So leaning into technology is really where it's at. Sort of our approach is really to lean in on the reality capture and the LiDAR to document and replicate the physical world into sort of a digital space that we can now analyze, we can break down, we can rely upon, and we take that right through to deliverables. Because ultimately that's what we are being sort of hired to do. We're not being hired to scan something. We're not being hired to create a digital twin. We're being hired to provide an opinion on something, some issue that's happening in the built environment. And so the goal is really to use this new and emerging and reliable technology to change how we collect data and provide better results to our clients. And a little bit of context here for our technology. Obviously, we definitely use our Hovermap STX. It is a fundamental piece to our sort of arsenal. We do have other LiDAR scanners available to us that are part of our sort of workflows. And something sort of to note in all of this, and we have that unique perspective, with being able to use a different piece of equipment for a different purpose, or, you know, or said differently, using the right tool for the right job. There are many cases where the Hovermap outshines other tools because of its versatility, its ability to be sort of used in a number of different scenarios, and the speed with which we can collect data. So we rely on that piece probably above all else, you know, more regularly, I'll say. But what does this actually mean to us? And it means that, you know, we have various objectives for our technology, and that all revolves around quantification and record keeping. What we're looking for are precise measurements, and we're looking for permanent digital records. Those 2 pieces are what we use to create our outcomes, which you're going to see, you know, sort of in the following slides. So I'll start by giving some sort of basic examples, I would say, of some of the things that we collect. You know, in most cases, we get called to a site to assess a facade or assess a roof or assess some part of the site. The first thing that we ask as consultants is, you know, do you have drawings? And I'm going to say 9/10 out of 10, we get zero feedback. There are no drawings. The image on your screen is typical for us where we're looking at a historic type building. There are no accurate records. Anything that is available is probably a representation of someone doing site measurements and trying to recreate a measured drawing. With the use of technology, we don't mind so much that 2D drawings don't exist, because once we've scanned it with our STX or any other piece of equipment that we have, we end up with a point cloud 3D model that we can actually analyze and use much more efficiently than any 2D representation that could be given to us. So data collection really is pivotal here. The idea of reality capture is that broader sort of idea of collecting real world information and putting it into a digital form is sort of the heart of what we're talking about. LiDAR and our STX is sort of the pivotal piece that allows us to do that efficiently. So some of these slides that you can see, we're taking data from the air, we can mount our STX to a drone, we can do things sort of manually by walking a site. I would say most of our scans are done via drone where we're able to fly, but in cases where we can't, we obviously we'll look for other means to capture the data. And that's really speaks to the versatility of the unit. And I know these are sort of images. I throw them up there only to really give some context. We're going to see a little later on in the presentation. We're actually going to start looking at some of these examples live, where you can see us manipulate a piece of data in our actual software. And that's really where this starts to come alive. The images that you're seeing don't do it justice at all. They look like pretty pictures that you could have taken off of the internet or Google or what have you. All of the things that you're looking at are actual sort of scans that we've created ourselves. None of these are sort of generated from the internet. So with that, I'm going to start talking about outcomes. So if you'll sort of roll back the slides in your mind to the slide of the measuring tapes. If you use LiDAR for nothing else, you can use it as a glorified measuring tape. Okay, you can take any sort of building. Let's say you're trying to do a plan of some sort. Take a scan, throw it into your analysis software. You end up with a 2D plan that you can dimension, and that's your outcome. But what's more than that, and what we've come to realize and what we are promoting to our clients, is the ability to take more information out of that scan. So for a simple building like you see on the screen here, we would have typically just gone to site, done a roof assessment. This is a roofing project where we're really just needing the plan of the roof, and we're going to provide a contractor with some dimensions and some instructions on how to replace the roof. What we've been able to achieve and what we're seeing more and more is that once we've taken that initial scan and created that point cloud, we can now start to analyze things that weren't there originally or weren't available to us just by the naked eye. So you can see in this case here, a point cloud is giving us some sort of a topographic view of what that roof is actually doing. If you zoom in and reanalyze it and sharpen the image, you get something a lot more valuable than just a 2D plan, where we can actually see high and low spots on a roof. Now, this is incredibly useful for us when we're doing roof analysis and trying to determine when and where and why we should be replacing the roof. I can very confident go back to my client and say, look, you've got high spots at the parapet where we expect, you've got a few ridges down the middle, and you have all these low spots that are colored blue. Now, in this particular case, the low spots are centered around drains, which is what you would expect. But let's say, for example, those blue low spots were somewhere on the roof that aren't expected. Well, now you have a case for doing something more than just replacing the roof. You have a justification. And really, that's where the analysis shines. It's justification. To take a roof scan using our Hovermap, strapped to our drone, this probably took us all of 20 minutes. I think it took us longer to drive there and set up the drone than it did to actually do the scan. But taking that information back, there's so much more value in what we've been able to collect that we can justify to our client why we want to recommend one action versus another. And from there, we started to really progress in, how detailed we can get into this analysis. What other things can we do with a point cloud as it relates to building and building envelope work? This particular example was an interesting one where it came to us through a contractor. We didn't actually design this roof, but we were asked to help them out because part of the problem for them was they had to replace this roof, and in their contract, it stipulated a condition where they wanted no areas of ponding water once the roof was completed. Now, if you're familiar with roof reconstructions and retrofits, there are very few instances where you could actually guarantee that a roof is going to be completely flat and there's going to be no areas of ponding water. We know this as building envelope consultants because fundamental to any roof reconstruction is the actual roof deck. That roof deck, if it's permanently deformed, is going to naturally provide areas of low spots. If you don't account for that prior to your design, you're going to have a problem, post-construction. So our solution here was very simple. Before they actually start ripping the roof off, we scanned it for them. And we created a very similar sort of topographic view that we saw on the previous slide, but for this entire area. This is a very large roof. If I remember correctly, it's over 100,000 square feet. But we were able to very clearly and accurately identify all of the areas where the roof was deflecting. The roof deck, I should say, was deflecting. So with that information in hand, we were able to produce a quick sketch or a drawing that could be given to a site foreman, whereby when they started ripping a particular area to do the sort of restoration, they knew that they need to bring extra material to level out those locations so that that deck would be flat, and from that base, they can create a flat roof. So this was a huge win for the contractor because they were able to work through this re-roofing project without worrying about whether or not they were going to miss an area because we gave them that information prior to their initiation of the work. Same thing happens when you start looking at even more complicated roofs. In this particular case, I know it looks small, but this was a roof where we had to do lightweight concrete for. And with lightweight concrete, it's a fantastic way to sort of iron out all of the roof deflection issues because you can slope that lightweight concrete any which way you want before you put the membrane on. But some of the hazards of that are once you've poured that lightweight concrete and you've shaped and formed it any which way you want, if you've missed something and it hardens and you put your roof on top of it, well, now you have an even bigger problem on your hands because in order to fix that, you need to fix the base before you can fix the ponding water issues. So the solution here was really, I think it was the next day, less than 12 hours after they did the initial pour, we went to site and we scanned the roof. And what that did for us is it allowed us to analyze very quickly after the pour how the concrete was finished and what the roof slopes looked like, was there accurate or enough drainage for the particular areas that we were looking at. And you can see in the imagery, red being high, green being at the level we want it to be, and blue being the lowest points. This roof, the higher roof, actually performed exactly the way that we wanted it to perform. All those blue squares are sump to drain locations, which we would expect to see. We can see high points down the center, which indicate a ridge, and we can see high points back slope at the perimeter. But what was interesting is that the lower roof, much smaller area, which we thought wasn't going to give us that much trouble, actually gave us the most trouble. So if you can see in that image there, there's virtually no distinction between high and low spots. It's pretty flat. And that's absolutely not what we had designed. We had designed something with perimeter back slope, and there was supposed to be a ridge somewhere where it was directing water to the two drains that are sort of in the corners. So in that case there, virtually the next day before the contractor demobilized, we were able to give them instructions to go back and add material, feather things out, and create the condition that we wanted them to create in accordance with our design. So incredibly useful in mitigating issues before they actually occur. Again, scanning at the right times, making sure that you're doing it in an efficient and quick way that you can actually provide instructions to someone so that they're not waiting around for a week or two. And again, technology is really helping us out here because this is not something we would be able to do manually. And if we could, it would take significantly more time. Now, where this really shines is our ability to actually do full detailed design and pair it with point cloud data. So we're using sort of this fancy terminology of design and clash detection. But essentially what we're looking at is the ability to take a point cloud generated through our LiDAR scan and pair it with a 3D model of our design. We usually do it in Revit, and see where things fit together. This has changed fundamentally how we do any sort of engineering work. The particular example that you're looking at on your screen is an elevator shaft. The client here was looking to recommission an elevator that had been decommissioned over 30 years ago in a building that's well over 100 years old. So naturally, the first thing that we asked for was drawings, and everyone laughed and said, no, that's not possible. You know, we had a bit of a chuckle and we realized it really doesn't matter to us because we're going to send our techs in there. Stephen, who's on the call, he's going to speak a little bit later on, was the one that went and did this scan. And essentially we scanned the interior and exterior of a shaft, and we created our own drawings. On the right-hand side of the page, you can see sort of the grid marks and grid lines we established based on the sort of dark interior line. We realized a couple of things right out of the gate without very much fanfare. You know, this shaft is not rectangular, which is, you know, not something that we fully appreciated initially. But what's more than that is that the shaft is not plumb. Now, you can't tell from these images, but that was a big find at the time that we did our point cloud, because in the sort of stakeholder discussions, the elevator manufacturer really needed some guidance on how to create the cab that could fit inside of this shaft. And if it's not rectangular and it's not plumb, you're going to have to, you know, really do a lot of site reconnaissance to figure all of that stuff out. In this case, they didn't have to do that. We threw our point cloud into Revit. We created a sort of fake elevator cab, and we adjusted that elevator cab in model space to sort of run through our point cloud and not touch anything. And once we had our sort of limited box, we're able to give those dimensions to the elevator manufacturer so that they could design their cab. And that progressed from there because we ended up designing the new penthouse. There's also some foundation work that we did. All of those things were put together to make sure that everything fit before we ever went to construction. So incredibly useful. Again, this is the kind of stuff that would take you know, several months to do manually. And from there, you know, it keeps progressing. Sort of one of the things that that we looked at for a similar client was a boiler room that you're seeing on your screen right now, where someone needed to get access to a valve that's sitting on the top of the tank all the way in the back of this, you know, very densely populated boiler room. This was actually a health and safety concern, which is interesting to us because we got asked to develop a series of stairs and platforms that would access this valve in this very sort of tight space, so that a maintenance worker who had to access this wasn't getting up on a ladder and sort of being put in a sort of risky situation every time they needed to service this valve. So it was a bit of a challenge because if we had to do this again manually, there's way too many things to be accounting for, and there are definitely no drawings detailing exactly where all of these pipes and valves and, you know, existing stairs and structure were. So we scanned it. We end up creating for ourselves the point cloud of the entire boiler room area. Now this picture doesn't do it justice. It looks like a jumbled mess, but I can assure you there were more pipes and wires and, you know, tanks in there that we could ever account for manually. Now, what this allowed us to do in our analysis software was start to design our actual sort of series of stairs and platforms, isolate pipes and valves and things, and then combine the two. And so what you're seeing on your screen is us sort of stripping that boiler room away, picking out only the parts that really matter to us, which is the interference of any piping in the vicinity, and couple it with our 3D model generated in Revit. So by doing a few of these iterations, we're able to come up with a design that did not interfere with any of the existing piping. So making those minor adjustments in this digital three-dimensional space, we're able to overcome all kinds of constructability issues that would obviously hinder this construction once we started fabricating. Now these went to fabrication, were delivered to site, bolted all together without a single problem. Again, one of our more successful projects from that point of view, because it went off without a hitch in a very, very complicated area. So hopefully this starts to give you a flavor of some of the things that we're able to do. And truth be told, we learn every day of how we can sort of push the technology to its limits. What kind of information can we gather? How much information can we gather? How do we manipulate it? The beauty of pairing this with our sort of consulting arm is that we get the opportunity to look at the technology from the point of view of how is it going to give me a result? Because ultimately that's what we need to do. We need a result. So, things like what you're seeing on your screen, we did a roof reconstruction. And one of the major concerns here is that we didn't really know, or the contractor didn't really know what was going on the underside of the deck. And for those of you who are familiar with re-roofing projects on existing buildings, there's usually a lot of stuff happening on the interior of the building, whether it's lighting, conduits, even structure that's in the way. If you're fastening something to an existing deck, you want to know that you're not putting those screws through anything, network cables or conduits or things like that. So we created a service for some of our contractors who were concerned about this, where we could scan the top side of a building, we can scan the underside of that deck, and ultimately take those images and really flip them around, sort of orient them the right way, tie them all together, and overlay them. And now this becomes a deliverable. This becomes a product that we can give to our contractors who are doing this roof work so that they can lay out where all of the conduits are, where all of the structure is from the top side with a known reference point. We could even take this a step further, tie to our TK and do positioning and lay this out with a basin rover for ultimate accuracy without ever having to take out a manual measuring wheel or a measuring tape or anything like that, or drilling a pilot hole and trying to figure out where you are from the inside to the outside. This eliminates all of that guesswork, puts everything sort of front and center in terms of what's relevant, and gives you the accuracy that you can rely on. And that's really where this shines. And it gets even better from there. So what we're going to do now is we're going to switch this over to my colleague, Steve Bruto, who's going to actually work through some of the projects in sort of real time. This is sort of a testament to the evolution that we've taken our technology and consulting, where we can actually start to use point cloud data and sort of the full point cloud and annotate it so that we can actually extract the information that we need to put it into reports to give justification for what we're doing. Really to the point where we're actually creating a real-time as-built drawing. And our belief from the consulting point of view is that as-built drawings eventually will be the thing of the past, and they'll be replaced with point cloud, because point cloud acts as a system of record for that point in time, and you can continue to annotate it over time, and you can add to it as things change. So we're going to see a little bit about that now. So I'm going to sort of turn this over, and we'll have Stephen sort of come online here.
Awesome. So I'm not sure if everybody can see my screen here, but we'll just kind of go through a few projects that we've worked on and kind of show you guys how we're putting this to work. Because it's really nice when you see it on slides, but it's got to go to work to really make it work here. So this here is a 16.5 acre asphalt plant. So outside of just building sciences and building design, we actually use this on a monthly basis for a client to do volumetric calculations of different aggregate materials. It's pretty standard to do this with drone work, but with the LiDAR, we're able to do it a lot faster and kind of stay in one program here. So after we collect the data in an automated flight with the Hovermap, we spend maybe about an hour and a half processing that data, and essentially we get meshes of all of these stockpiles with high accurate data, and it actually generates a report for the contractors and asphalt plants to kind of go through. I might have Daniel speak to it a little bit here, just because it's hard to turn everything on and off as I also speak to it. But.
Sure, I'll jump in while you're sort of panning around there. But this is sort of an example of the base use for our hover map, where we're really not doing anything from the point of view of engineering. We're really just providing a service to a client that needs information. This is the kind of thing that, yes, you could do manually. It's been done manually in the past. You would probably get a surveyor out there with a total station or a basin rover, sort of walk all of these piles, take measurements from the top and all the way around, and create for yourself a mesh so that you can estimate volumes. Well, with our hover map mounted to a drone, we don't have to do any of that stuff. But most of the time, the site actually doesn't even know that we're there. We park somewhere down the street, we fly our automated flight path, and we pick up all the information that we need and head back to the office. Steve can correct me if I'm wrong, but this is a process that from start to finish and report in with a report in the client's hand is less than 4 hours.
Yeah, so we do multiple sites in a day, and it's always on the last of the month. And yeah, it's not exactly what we advertise as much, but it makes it so easy with the Hovermap that this is a client who actually we do asphalt design with them, and they've seen what we do for parking lot extensions and everything, and they just asked if that's something we can help them out with. And it's so easy with the Hovermap, we said, sure, why not? But I'll jump into the parking lot expansion ones.
Again, these are, you'll start to see sort of a progression with the projects that we're showing you. The asphalt plant is really one use case where you're talking about really using the tool for a particular purpose, and it's really just being relied upon to give accurate information. But for the same client, we can do more things, like extend that technology and use it for creating actual designs for parking lots, which is what they do. The images that you're seeing on your screen and the analysis that we're doing here, this was a parking lot extension where we needed to add to this existing parking lot. So part of the workflow was very simple. Before we did a single thing, we sent Steve out there to scan this all and then bring back the information so that we can get topographic information. Well before we even needed to ever consult a surveyor, because we can tie all of this information into known data points and get sort of the GPS sort of locates as we need it.
So with this one, we did the drone-based scan, so it was the Hovermap with the Trees 350. We did again automated flight path, but not too long at all. And then we also went around with the Hovermap and the handheld attachment, because the area that they want to extend into this is a drive lane here, and they're adding parking spaces kind of in this boxed area. So we're able to get, because it's a ditch, we went in with the handheld to get the existing curb on the back side. First, we produced a topographic survey of existing curves, and then within this point cloud, we were actually able to do translations to move and extend the existing curve into that proposed location. So it's the same profile of the curve, but we manipulated it in like a digital world. And because our contractor is also, I would say they've invested in technology, all of their machines are equipped with machine control. So these polylines were able to be exported into a CAD file and loaded directly into their excavators and spreaders and bulldozers and stuff. So what we did is we localized the site using ArcVK based on a couple of features throughout the site. So we used manhole covers, catch basin covers, kind of called out all those coordinates with the northerns and eastings. And then our contractor went around and localized our CAD file to the site in real time. And that allowed them to plot this, this proposed curve with centimeter level accuracy and load that CAD file into their machine, so then their operators have full machine control while they're doing this. And they love it because honestly, it's a lot easier than giving them a 2D drawing where what normally happens, and then they're doing layout off of existing curves and measuring out, then it might not be square and straight. And because we're designing in a digital one-to-one replica, and we pass that on to them with a localized file, they can lay out the curve a lot easier than they ever used to. Right?
And just to add to that for a minute, what we're really talking about here is a full integration from sort of assessment to design to construction. That's sort of the crowning achievement of what we've been able to get to, where it's not just about the engineers and the consultants, gathering information and making sort of more accurate or educated decisions, but it's about extending that towards the contractor and tying into their own systems so that there's a seamless transition of information and everyone's looking at the exact same thing with the exact same vantage point or perspective, with very little room for interpretation. That's where this sort of really comes to life.
But then I'll jump into this one next time. Something that was kind of used exclusively in that world of paving and topographic scans, we were able, again, showed during the presentation, bring that into a much smaller scale that it typically doesn't exist, and that's into roofing. So this was a project with a roof that was just littered with solar panels, and they had some issues with ponding. And I'm not sure if it's because the space below was just very open, but it was a contractor to client relationship, and we kind of got brought in separately just to assist. But their solution was to add drains in the areas that are ponding. But because of the solar panels and some difficulties on the other side, on the visible side of the roof, they didn't really know how to find the areas that were best for that. So what we did is we scanned it again with we used the M350 with the Hovermap on the drone, and we scanned it with the drone. And then we actually went on the roof as well and walked it with the handheld, so we can stick the Hovermap in the small areas of all the solar panels. That allowed us to grab the solar panels separately and basically work on a roof that doesn't have solar panels, right? So we can remove those, turn off our roof, turn on our elevation data. And then all of this allows for us to also add contour lines. So it looks a little busy, but busy is good because it's a lot of data. This allowed us to, without a doubt, tell the contractor 5 proposed locations that we know the surrounding areas within at least an 8-foot reach in every direction will be grabbing water and pouring those into those drains. So when he presents this to his client, although again it looks a little busy, it shows that our drain locations are backed by data, and it's not just, because it may pond in an area, but the water traveling to get there, instead of water running all the way across the roof, we can look at the pathway that the water is taking to get there, put a drain in that area, so it helps with, instead of the water going from one end of the roof to the other to a drain and catching, if it's like a mod pit or something, there's a lot of degranulation along the way. If we put a drain in that pathway, it kind of stops it at its source, and then we put some at the end to pick it up. So instead of just putting it where there's a puddle, right? You can kind of see where it's running through, which way its path is to get there.
And so hopefully what you're gathering from this is our ability to really analyze things from multiple vantage points. And not enough anymore to give years. But when you can justify that opinion with sort of accurate data and images, I respond much better to it. And that's where we're finding a tremendous amount of success.
Okay, jump into.
While you're transitioning, I can ask you just one of the questions that have come in through the chat here. So you mentioned that you use RTK to correct those scans. How do you handle areas without GNSS reception?
Okay, so that's actually perfect for this one. So okay, so I'll answer that and I'll demo a little bit here. So this was a 250,000 square foot warehouse office space where it was a roofer concerned about his mechanical fasteners going through the metal deck and piercing conduit. So what we did was we scanned the inside and the outside. So we did the inside with the Emerson and the backpack, and the outside with the 350 and the drone. From there, we were able to use the RTK from the drone and the outside scans. So even though we did 5 or 6 scans because the building was so large, what we did is we overlapped our point cloud. So when we finish one scan, we make sure that it's in a common area that we'll start the next one in the same area and do that merge within Aura. And because our scans outside are all tied into RTK and our cloud-to-cloud alignment is so strong, the points inside that don't necessarily have GNSS receiving, they still have coordinate systems that we can trust because the merge had such a high tie-in rate. So the conduits that we have here, I'll throw my limit box on. So it's a huge building, but and a lot of data that sometimes takes a second to load. But all of this blue, so this here, this was electrical conduit on the underside of the deck. So when you zoom in, it looks, somewhat easy to see, but we were able to isolate this and draw polylines on all of it. So those are junction boxes, and what we can do is we can translate these polylines to the outside of the building, and all of these polylines, although we don't have RTK or GNSS, all of these polylines, again, are tied into that coordinate system that we set locally. So we can go on the roof with a Basin rover afterwards and localize off of a CB, which was caught thanks to the drone scan, and put this coordinate system onto the site and lay out these conduits on the roof with, again, centimeter level accuracy and just orange marking paint. So as the roofer is working, he knows everywhere not to put a fastener. But yeah, so that's kind of a bit of both. That's how we map the conduit, and that's how we work in areas that are GPS denied. Generally, we can also locally. So even if we don't have GPS, technically, all of our designs, as long as there's something there, you can use targets on walls or if you're in tunnels and stuff. As long as when you go back to do layout or whatever you need to do, you calibrate yourself off of those targets, you can still operate with a really strong, accurate coordinate system. Looks like Daniel's kind of popping in and out here a little bit.
I think we've lost him. Hopefully he can get back in. But another question that was asked was just what software are you currently using? Maybe you can just expand on that a little bit.
So the software that you guys are seeing right now is a Leica software. It's called Cyclone 3DR. We use this for our analysis, I would say. So we do all of our processing and cleanup in Aura, and our control points and tie-ins and stuff like that all exist within Aura. And then we kind of switch here for any kind of We also work heavily in Revit as well. So we'll import these point clouds into Revit, and that's kind of where our modeling ties in with existing space. And then any models that we do create in Revit can also be imported into 3DR here. And we can kind of use the best of both worlds. So. Daniel, you're back.
Yeah, in the course of that explanation, you kind of answered one of the other questions there, Steve, which was, do you use ground control points? And I think that the answer to that is yes, and it sounds like it's a little bit situationally dependent, based on whether or not RTK seems appropriate or feasible on the scenario.
Yeah. So if we're outside, we'll generally use RTK. It depends on the process. So if we know we're submitting for topographic surveys, then we'll tie into known coordinates and known benchmarks as well as our RTK. But if we're working on an interior environment, then we'll just tie into our RTK data from outside. Or sometimes we'll just work locally. So it really depends on what the outcome needs to be. Another one here. So this was another one that was shown during the presentation. We'll be quick with this one, but just give you a show and feel for it. So this was the space that we scanned, and this is, so another thing that's good to talk about is colorization. Colorization is sometimes important, but in this case, we were able to skip the colorization and just go into classification. So each of these different colors are different aspects of the building, so pipes and wires. And it's not perfect, but it depending on what you're after, we kind of focus on that. So in that area, we were focused on pipes. And we can isolate those pipes, turn off anything that we don't really want in there, and then bring our BIM model in from Revit. And at that point, you can start to see and measure any areas that do clash. I think this is the final version that we finally submitted with it, but yeah, the BIM models work seamlessly in here with the scan. And I think this was a mix of scanners. So we have tripod scanners and we also have Hovermap. Hovermap's really nice in situations like this because if there's areas that you have to specifically get to, you can kind of take that and get the handheld and take it to a pole if you need to and wrap it up and around all the pipes and shove it in all the corners. Like the, I guess that was another thing I mentioned. In the conduit scan that we did a little bit earlier here, a lot of this area actually had ceiling tiles too. So we wouldn't have been able to do this with really any other scanner other than the Hovermap. So we had to pop all these ceiling tiles out, every 3 or 4 ceiling tiles, and shove the Hovermap into dark spaces. But, similar to that is the boiler house. So wrapping this around pipes and using the versatility of the Hovermap just to really get into all the areas that are hard to reach.
Steve, I think the technical term that you're looking for is it's good for confined spaces.
There you go, confined spaces.
We're gonna clip that tagline. I couldn't have done this without anything other than the Hovermap, right?
Yeah. Yeah, honestly, I don't think we could have though. I mean, I couldn't even see in there. A lot of those ceiling tiles, I pop my head up in, I'm coming out covered in white dust, and I'm hoping that the Hovermap got it. And it was, an hour and a half away from my house, and I finally get home, and I processed it in Aura, and I could see all the conduits. So I even called Daniel at one point and said, I don't know if it's gonna work because I couldn't see any conduit when I stuck my head in there. So.
And that leads to another good question, which is how do you take that data from Aura, I guess, and then bring it into the software that you're working with? What's that process like?
Yeah, so I'll process in Aura. It publishes. So when I do the merges, I mean, I guess no matter what, it publishes an LEZ file, is what I have it set up as, and then from there I can basically just drag and drop into 3DR. There's different parameters for, sometimes it wants you to convert to different file formats, LGSXs and stuff. Sometimes we'll use a Hovermap scan and we'll use a Leica scan. And actually, I think this one is a Hovermap scan and a Leica scan. But it doesn't always love that, so you kind of have to trick the system with the coordinate system that you use. So generally, we'll keep the coordinate system that's created from Aura because if you did 5 different scans with the hover map and you link them all together in Aura, that merge file creates a new coordinate system for your 5 scans. And we actually don't do, I don't know if it, well, we don't do the last step that's recommended in the knowledge base. So the last step is to open all files and then save as one. We actually like to keep it as 5 different files with the same coordinate system. So that's kind of what happened here. So we have DR whole office, training office 2, LAZ, drone scans. But we keep them separate because they have the same coordinate system, and it's more valuable for us to be able to toggle those on and off. And yeah, the question was, how do we get them in? LAZ files, we drag and drop LAZ files. Sometimes we convert them, but
just to add to that, a lot of this process that we're working through is heavily influenced by data management. Okay, there's a lot of data that's being collected. It takes up a lot of storage. It takes up a lot of bandwidth on any one machine that we're using. We've upgraded our computers and processors, I think 3 times since we started this. It really is process heavy once you start combining lots of different scans and types of scans, and especially once you get into more in-depth analysis, your infrastructure really becomes a limiting factor. So it's nice to grab the information with your hover map, and it's nice to have, but if you cannot efficiently process the data, you're going to have a hard time. Aura has been very instrumental in helping us sort of take the data, process it, strip it down, sort of manipulate it before we need to get it into sort of an analysis mode. Sort of Aura has worked wonders in that. It seems to be very efficient in what it does when it's sort of registering and processing the initial scan. But definitely we need to take a lot of steps in order to get it to a point where we can actually use it.
Yeah, it's definitely very data heavy, and the more you do to a file, the worse it gets in terms of data heavy. So like Aura, when files first come out, depending on scan time, I'm sure there's actual statistics for Emerson, but yeah, if you do like a 20-minute scan, it's a couple of gigabytes for sure. And then when you start manipulating it and adding meshes and slices and copies, a lot of these files, we did, I can't even open it because it's just too big, but we have one file that's like 620 gigabytes of an island that we scanned, and it's huge, right? So you have to be big on data management. This is another example here where we did a building envelope assessment, but instead of just walking around taking photos and giving them a Word document report, in addition to that, we're actually able to walk around, take photos of deficiencies, but later we come back to the point cloud and we mark up each of those deficiencies and tie them geographically to the building. This allows us to, I don't know if I can actually open each one, but each of these numbers here are deficiency. So I have my sharing screen kind of blocking it, but you can tie images to it as well, which sometimes, again, with data heavy, the images don't always stay. But what we did here is we separated all of our deficiencies. So if it's window replacement, brick replacement, we can split that cloud into a bunch of different groups. So this is basically everything that we determine needs to change on the building. And then from there, you can mesh every single one, which might take a second to open because meshes we find to be really heavy. And then turn on measure groups. And again, looks crazy, but each of these is a square meter measurement. So if we're doing brick replacement, we know that in a standard square meter of brick, there's 16 linear inches or something of grout. We have all the numbers set aside, but from this quantification, we're able to calculate things that we couldn't really count before. I mean, to measure a lot of this stuff, you'd be setting up scaffolding and ladders, and we just walk around with the hover map, and yeah, I don't.
Yeah, it might be good to go from this screen, Steve, to an actual output file where it actually looks like something we would deliver to a client.
Yeah.
yeah, maybe you want to scroll down there a bit, and you can sort of see, ultimately, like I started the presentation with originally, was we have to deliver something to our clients. And this something is usually a report, which is what you're seeing on the screen here. It's a very typical report. You've got photographs, you've got annotations, descriptions of things. But this report is enhanced by the fact that we've used our point cloud to do the analysis, because we add to the end of this report an appendix. And the appendix is really where all of the information is held, because now we can take screenshots from our point cloud. We can show the annotation of the point cloud with the measurements. We can break it up into very specific things or components that we need to address and draw attention to. So when you take the traditional report and you enhance it with this type of technology, and then you add the benefit of the point cloud, which never goes away, you have a very powerful system here now where you can accurately, efficiently, convey information to not only the stakeholders, the owners of the building, the operators of the building, but also the contractors who are trying to do work. It's very easy now to hand this appendix, and maybe if you stop on one of the pages here, Steve, I can sort of show that I could essentially hand this page to a contractor and say, okay, well, here's the numbering sequence, here's the deficiency, here's the description, here's the priority with which it needs to get done. Refer to the image with the point cloud. You can literally go to site and point to it and have it refer back to something on a piece of paper that looks accurate and instruct the contractor accordingly. So again, from a conveyance of information point of view, there is nothing better, in my opinion, to be able to show a contractor an accurate depiction of what's happening and point to an area that's been quantified and instruct them accordingly. This is the fundamental basis of everything that we do. Now we're just doing it in a much more, I'll say, intelligent way.
With that, I think we're kind of at the end there a little bit. 2 minutes left.
Yeah, we're running out of time here, guys. So yeah, thanks so much. I mean, that was really great, really informative. So thanks for taking us through what you do. I think we've covered all the questions. So yeah, I really appreciate everyone's time for tuning in here today. This session, like we mentioned at the start, it is recorded. So if there's anyone that you feel would like to see this, please share that with them. And stay tuned for future MSN webinars.
Yeah. Awesome. Thanks for having us.
Thanks for having us, Daniel. Appreciate it.
Thanks, guys. Our pleasure.